This conference.
Okay, so welcome everyone. Today we'll have a presentation from our friends at NetTimeLogic, and it will be basically about the source code of the FPGA of the time card, which I know a lot of you guys are who are involved with the time card and like all the design, everything. I've been always asking for it, so I think the waiting is coming to a point where you can finally see when we can get like what is basically under the hood and when we can get basically to the source code. So quickly introducing our speakers, we have Thomas Schaub, which is a business partner and principal FPGA design engineer at NetTimeLogic. He holds a bachelor degree in electrical engineering and information technology. Since the last 15 years, he's been involved in development and utilization and printing industry in deterministic and high reliability requirements. And also we have Sven Meier, which is the managing director and lead FPGA design engineer at NetTimeLogic. In 2015, he founded the NetTimeLogic with a goal to develop best-in-class FPGA IP cores, which can be integrated as kind of a co-processor handling the different protocols directly in hardware. He holds a bachelor degree in information technology and a master of advanced studies degree in business information technology. So over the last years, he developed several FPGA IP cores for synchronization, Ethernet redundancy, and time-sensitive network. He's also a part of the standardization group of IEEE 1588 and IEEE 802.1 and created several papers in this area. It's a pleasure to have both of you guys here, and with no further ado, the floor is yours.
Great, thanks a lot for the introduction, and also welcome from my side to the presentation about open source, the FPGA design for the time card. Okay, good. Today we will talk first about the time card itself to give all of you a short introduction what the time card is and how does it work. Then we will talk quickly about the current FPGA design. We will show you also the way to open source, including a timeline, and then we have also room for discussion on the inputs from your side. Okay, what does the time card? The time card is the heart of the open time server. There is basically the time card as a card for PCIe slot, which is connected to a host PC. In the server, there is also an off-the-shelf network adapter, which can be synchronized over PPS. So the main task of the time card is to synchronize to GNSS. Then it has also the job to maintain the accuracy in case of holdover. So if you lose GNSS, for example, the time card can maintain the time with a very high accuracy over a long time. Then the time card can provide the time, the synchronized time via PCI Express to the host system. This is done via a PHC driver. This synchronized time can then be also forwarded to the network adapter. To precisely synchronize the network interface, there is also PPS required. So we go externally with the cable to the network adapter. This approach allows us to connect theoretically any network adapter or network card off the shelf, which has just a PPS input and can therefore be used for PTP synchronization in any network. And we have no restrictions, let's say, in the time card for the interface speed here. So if the interface speed here increase, just switch the network card, but the time card is still the same. For the time card itself, there is a FPGA bitstream existing, and this bitstream is as freeware available. Now let's talk quickly about the current FPGA design. The main functionality of the FPGA design is that it's able to synchronize to a GNSS receiver. This is fully done in hardware, so the time from the messages is extracted in hardware. The time of day is then provided to adjustable clock. Additionally, also fully in hardware, we synchronize to the pulse per second, also the one from the GNSS receiver. The time card then can provide the synchronized time in time via PCI Express to the whole system. As I already mentioned before, we also provide the pulse per second to synchronize any device on an output. So this pulse per second can be fed to an output and then connected to a network card. There are also several other selectable options for synchronization sources. For example, we are supporting IRIC as a slave. We can DCF be synchronized, or we can just be synchronized to a simple pulse per second from external. Additionally, there are also quite many options which can be selected to provide our synchronized time as an output. So we can feed out the IRIC information, the DCF information, or as well just a simple pulse per second. Now let's talk quickly about the IP cores which are included in this design. There are several cores from Xilinx which were available, for example, the PCI Express bridge, GPIO modules, I2C interfaces, stuff like that. There are also quite many custom cores which were developed during the whole project phase. But the main part or the main functionality is provided by NetTimeLogic IP cores. This is done in that way just to accelerate the project, and these cores were just available. So we have just integrate them into design out of the box, and we were quite fast to provide a running system. This FPGA design is at the moment only available as binary. So this means we provide a bit stream, but this bit stream can be used without any restriction. So you can take the time card, you can load your bit stream, and the design is working. However, this has not, of course, some limitation that there are no user adaptation possible since the source code is not available. So you cannot put just some custom parts into the design and build it for the time card. Now let's go a bit deeper into the IP blocks in the FPGA design. Here on the left side, you can see the time card. Here we have the GNSS receiver with an antenna connector. And here we have 4 SMA connectors which can be used as input for time sources, or we can also provide signals over these SMA connectors. On the right side, you can see the complete block diagram of the FPGA. I will not go into all the details of these different IP cores here, but I just want to quickly highlight the different coloring here. So we have the light blue ones, which are Xilinx IP cores running on 50 megahertz. We have here a dark blue one, which is the Xilinx PCI Express bridge, which is running on 62.5 megahertz. Then we have dark gray IP cores, which are NetTimeLogic cores running on 50 megahertz. And then we have also light gray ones, which are running on 50 megahertz and on 200 megahertz. The 200 megahertz part is required to get a smaller granularity of the timestamp. So this is a small high resolution part, which allows us to improve the precision a lot. The white ones are the IP cores which we have developed during the project. I will now quickly show you the main synchronization path of the whole design. So as we have seen, we have here the GNSS receiver. The GNSS receiver provides via UART UBX messages. These UBX messages are provided to a Xilinx UART interface, so this can be accessed by software, or it goes directly into the hardware part, our TOD slave. This TOD slave extracts from the UBX messages the time of day information and provides it to an adjustable clock here. The second part is the pulse per second. So we have here the pulse per second from the GNSS module, which goes to the PPS source selector. The PPS source selector automatically selects, depending on the availability of different PPS sources, which pulse per second is provided to the PPS slave. So let's assume now we have a GNSS PPS pulse here, then this pulse is forwarded to the PPS slave. As well, it's forwarded or feeded back to the Mac to discipline the Mac as well. If the PPS from GNSS is gone, we jump over to the Mac PPS input. The PPS slave synchronized to this PPS and provides adjustment to the adjustable clock. The adjustable clock is responsible to maintain the time of the whole system. So this clock provides also the time to many other cores, which then is used, for example, for timestamper. The adjustable clocks provides the time. But here only one main part is highlighted in green, the one which is going to the PPS master. This signal then is used to feed out to a SMA connector and can, for example, be used to synchronize the network card. Yeah, for completeness, here just a short overview what IP cores are all in the design. On the left side, you can see all the IP cores from NetTimeLogic, and here also how many times they are instantiated. For example, there are 5 timestampers instantiated. In the middle, we have all the cores from Xilinx, so UART adapters, GPIO, PCI Express bridge, stuff like that. And on the right side, we have also the custom cores, which are instantiated in the design. Yeah, since you saw now that we have different, let's say, IP cores in there, we have also quickly talk about the conditions. So there are quite many Xilinx IP cores in. They are all free to use. However, source code is also not available for them. For the custom cores, they are already open source. We have just not pushed them to GitHub since they are not really useful without the other parts of the design. Then we come to the NetTimeLogic IP cores, which are property of NetTimeLogic. So they are available as part of the complete binary for the time card, and it can be used without any restrictions. So the full functionality of the core is integrated just for the time card. These IP cores theoretically are requiring a license per user or per customer for a license fee. And that's the reason why this source code cannot publicly be available, since all the customers have both this code. Additionally, of course, this is somehow our business model, that we want to sell these IP cores, which are very generic in a modular system for several approach designed with a lot of configuration, which is even not needed now for the time card. So yeah, as already mentioned, this is not the idea. So we will not make these IP cores which are available as open source. But yeah, now let's talk a bit how the way could look like to open source. So for us, it's fully clear that it makes sense for the OCP project to have open source space as well for the FPGA, to allow the users to extend the design, to create their own designs, that they can modify something, integrate, I don't know, more timestamp or whatever they need. The Xilinx core will also not be open source, but at least free to use. So that's quite easy. So it's also straightforward. They can be integrated in a block design, and all's good. Yeah, for the NetTimeLogic IP cores, we will create a replacement as an open source version, which is providing the same functionality and doesn't look different from externally, but maybe not that generic and modular usable as our cores in every combination. The initial base will still be developed by us, by NetTimeLogic. Yeah, now I've started already talking about the open source way, but yeah, what happens with the current design? Yeah, the current design is already widely used, so the time cards are running with the bitstream on it. So we will maintain the current design as long as required. It's still an easy way to get the time card up and running. So you can just take the bitstream, load it on the card, use the existing driver, and you have a running system with the synchronizing time card. If someone would like to create modifications, known design, needs source code, whatever, there is still the option to buy the source from us, so this is not a problem at all. So yeah, and then you can also create design fully from scratch. You have the block design, you can modify whatever you need. And now go one step back again in the current design. So yeah, we have seen there are a lot of IP cores from NetTimeLogic in, but not all of them are required for the time card primary functionality. We have instantiated quite many cores like IRIC slave, IRIC master, some frequency counter, and a lot of stuff like that. This was just done on request for special purposes and to create a system which covers as many use cases as possible. This was quite easy for us since the cores were already available and we have only to instantiate them. So that's the reason why there are much more cores in the design than really required for the primary functionality. In addition, some of the functionality would be also possible to cover in software. For example, the frame parsing is now done fully in hardware, which is, yeah, let's say a bit an overkill sometimes for just analyzing data which is coming via UART. This could be easily done in software. Also, adjustment of the time of day information of the clock could be easily done in software. We have also an NMEA master in the design. This is also a part which can be done quite easy in software. So there are many modules in which not are mandatory to made in an FPGA. But yeah, as already said before, we had this core already available. It was just putting it together, integrated, and it was up and running. Good. Now we will really talk about the way to open source, and I will now hand over to Sven. I will give you control. Hopefully it works. Is it okay?
It should be transferred now.
I have control now.
Oh, transferred. Okay.
Oh, transferred. Okay.
Oh, do you want to stay as a presenter? Either way works.
So you see the slides again?
Yes.
Okay, very good. So yeah, thanks for the introduction of that one. So now, yeah, we are really going into what we're going to plan for the open source thing, and we have a slightly different approach, at least for the beginning, for the open source version. As Thomas already mentioned, there are a couple of things which are in the FPGA which not necessarily need to be in the FPGA. So our plan is that we're going to have a base system and an extended base system. And for the very first base system, we will only implement basically the functionality which is really required for the time card's primary functionality. And also only those parts which are really time critical and kind of need to be handled by the FPGA. Yeah, as Thomas already said, so NMEA or UBX frame parsing, for example, can be done in software. And in fact, the current design is already prepared that we could do it in software, but yeah, since we had the hardware solution, it was probably handy to just use the hardware implementation and not do the software implementation, but it can easily be basically moved to software. This has a couple of advantages. So first of all, yeah, it will reduce the number of cores required in the FPGA, which one feature or one benefit of that is that it is for us less effort to implement that as an open source version. And probably more interesting for everybody else is that it's going to use less resources on the FPGA. So there is more space available for user-specific code, whatever that will be. The second point, which is kind of important, is it gives you much more freedom to kind of adapt functionalities, for example, filtering, or even a lot of long-term statistics and stuff like that, which is kind of impossible in the FPGA that you could do on software, and all that without requiring any change on the FPGA side. So yeah, what will we provide? So first of all, we provide the base system. Yeah, so it is intended that the community can further extend the functionalities of that time card. And of course, if they do extensions, everybody would probably highly appreciate if they would put it again as open source to the GitHub repository. Yeah, what our base system, or what the base system really shall provide, is the primary functionality of the time card. So it shall allow to synchronize to GNSS via UART, the serial stream from a GNSS receiver, and for the time of day, and then having the PPS for frequency and phase adjustment. And yeah, as well, time-stepping external events or pulses like PPS or pulses and measuring frequencies, and on the other side going for outputs, generating timed events, again pulse per second or pulses. In the end, yeah, it shall be a living ecosystem where everybody can kind of contribute to the time card open source project, and yeah, maybe add again those functionalities which we don't see as the base functionality, like the IRIC part or the DCF, or yeah, whatever you come up with. One thing to mention here, the open source course will be available under the GNU Lesser General Public License, so the LGPL. In the sense of FPGA development, that means yeah, you have basically no restrictions if you connect to some of the IP cores. It's kind of, yeah, dynamic linking is not possible in the FPGA, but it's the same way, so you don't need to make your specific part public just because you have used some of those IP cores in the design. The changing concept, I just mentioned that NMEA messages can be synchronized, can be also parsed in software. I give you the short version of it. So basically, we have an FPGA core in there, pulse per sec, NMEA UBX. So UBX is the MuBlocks protocol from, yeah, MuBlocks. Slave core in there, which parses the messages which are coming from the UART. It extracts UTC time and leap second information, and basically takes those two things to convert UTC to TAI, and in the end sets the adjustable clock in the design to the right seconds. So this way we get the time of day on a granularity of seconds, and this is all done in the FPGA directly, and the software can basically just do some configurations and do some status supervision. For the open source design, we planned a different approach. So we're going to have Xilinx UART core in the design, connect that to the GNSS receiver. So the CPU basically receives all those frames. Parsing in software is anyhow much easier than doing it in the FPGA. So the software will parse that for, again, the UTC time and the UTC leap second information, calculates again the TAI time out of it, and will use that TAI time to write it down to the adjustable counter clock, which will still be in the design, and overwrite the seconds part of it. So that's for the time of day. For pulse per second synchronization, again, we have a core in there. It takes a timestamp on a rising edge of the pulse per second, calculates the frequency and phase difference to the local time that we already have, then filters those frequency and phase differences through PI server loop to filter out a bit of the jitter, and then adjusts the adjustable counterclock core. The adjustable counterclock core itself spreads adjustments evenly over time. So it's a numeric adjustment. It's not like pulling on a frequency or something. It's really doing numerical adjustments, but spreads that over time. For the pulse per second synchronization for the open source design, so with the software approach, we're going to have a timestamper core in there, which again will take a timestamp on the rising edge of the PPS. Then the software calculates the frequency and phase difference between the pulse per second and the clock. So basically the timestamp should be somewhere at the 0 crossing of the seconds. If it's not, it has some offset. If you have 2 timestamps, you know that the frequency, there should be exactly 1 second in between. If that's not the case, your frequency is either a bit too fast or too slow. So basically you have that information as well. Then you can do as well filtering, can be a PI server loop, it can be more sophisticated statistics, whatever, to figure out basically what you want to adjust on the clock. And then you can basically write down the adjustments to the counter clock to adjust the frequency and phase again, which will again be spread evenly over time, since that's the same core as in the current design, basically. So there are a couple of functionalities in the base systems, which are not there compared to the current design. So we will not support IEEE either as input or output. The same applies for DCF77. Yeah, that was just not the base or the main functionality of the time card, so we skipped that part. But on the other hand, we have some additional functionalities compared to the basis, compared to the current design. We wanted to also make it possible to like daisy chain or even like spread over multiple time cards, basically the information of GNSS. So you can basically feed the UBX or the serial data stream from a GNSS receiver directly to SMAs. The CPU anyhow receives the GNSS messages, but it can also recreate some GNSS messages if it wants to. And so you have on the SMA connector basically inputs for those serial streams to, yeah, you could basically daisy chain a couple of time cards together. Then the other change that we made or additional functionality that we really want to add is we want to have it modular, and especially for the purpose of the community extending the design. We wanted to add a core list with entries for each core instance, which contains like a core type, an instance number, versions, base addresses, interrupt numbers, maybe a magic word that explains the functionality, like the PPS SMA1 or PPS GNSS or whatever string it shall be. The idea is that the software in the end can figure out dynamically what's instantiated in the design and how to interact with it. So that's the idea behind it. Yeah, we also made ourselves some compatibility constraints. So we considered that the register set of the open source course shall really be identical to the existing course, because yeah, we want to maintain the compatibility of the existing driver and the new FPGA design as much as possible. So the initial design will have also the base addresses of all those cores at the same offset, so you could really load the driver and it should work out of the box. Also, we wanted to again have the open source course FPGA vendor independent. The time card as it is now, it has a Xilinx device as a system on module up there, but yeah, we don't want to limit it to this. This will basically allow us that you can port the open source course directly to any other FPGA vendor's design, because it's going to be pure VHDL code. The downside on that is if you want to switch, for example, to a Altera Intel microsemi device, only our cores are vendor independent. So of course the PCIe bridge, SPI UART controllers and all that, these are strictly bound to Xilinx and FPGA vendor dependent. So you need to search for a substitute for the specific FPGA vendor, and yeah, the driver needs to be adapted accordingly, because that one expects Xilinx drivers currently as well. Yeah, and our concept changes also require a bit of software adaptation. So mainly the software support for the GNSS synchronization should be prepared for the open source FPGA implementation. And yeah, the other point is more looking into the future. So we would like to see that the driver is more modular. Currently it's a one file driver, and we would love to see it split up into multiple ones, and the one main driver which basically fetches the core list and then define based on that loads different drivers according to the cores in the design. And this would make it very generic and extendable for new cores to arise. So yeah, now we're coming shortly to graphic again. It's kind of similar to what we've seen before. So basically, I just colored two things: which ones are open source cores and which ones are going to be the Xilinx IP cores. The concept, Thomas already explained it. We just have some more signals going from the GNSS serial streams or some UARTs feeding which have some paths to the SMA selection, so you can feed or receive GNSS messages via also an external cable. The list is similar to what we've seen in the current design, except of the PPS slave and time of day slave, which we used for the hardware synchronization directly. So yeah, I said there is a base system and there's going to be an extended base system. So what will we have in the extended base system? It's again the pure hardware functionality to synchronize directly to GNSS. So having a time of day slave, parsing, adjusting seconds, PPS slave, adjusting frequency and phase. That will be added again as an extended base system to the design. We'll do that as a second step, since it's kind of not essential for the base functionality, because we can synchronize to GNSS via software, so it doesn't have to be in there. However, it is of course a nice feature, and it distinguishes the time card from other solutions. So you just connect the card to GNSS and you get a synchronized time out of PCI. You can just read the synchronized time out of it. So therefore we will add that feature again, but without removing the base support. So one can choose whether he wants to use the software synchronization or the hardware synchronization, depending on its needs. And yeah, nobody is enforced to use the hardware synchronization. They can still use the software synchronization if they want, or the other way around. So yeah, just added a little picture of those two additional cores that we're gonna add. So it's just a PPS slave and the time of day slave. They're getting PPS as the timestampers basically, and the TOD slave gets the UART as the Xilinx UART would receive it. They just have adjustment outputs which directly go to the adjustable counterclock within the FPGA. So there's no software loop. It will directly adjust the frequency for the clock for frequency and phase and the absolute time. Coming to the timeline, the base system, which needs software support for GNSS synchronization, at least the FPGA part, we plan to have it latest mid of June this year, and the extended base system latest mid of September this year. We already started with the development, and so far we're really on track. And the plan is that we will release the cores gradually once they are completed, also to ChipHub. And now, we're coming already to discussion and input. So our question to you: are we missing something? Do you need a feature? Are we really missing something that is essential or stuff like that? So it's an open question.
Okay, so you can either unmute yourself and ask your question directly, or I don't know, for whatever reason, if you don't have a, let's assume you don't have a microphone. It's not shyness. Put it in the text and then I can read it for you. So let's start with that. Like anyone, any question? Maybe icebreaker. I will start with the questions. So Sven and Thomas, like first of all, thank you very much for the presentation. The first question I have is, if I want to go with, let's say, other than uBlocks, other GNSS, let's say, I don't know, other things that are in the market, I definitely need a different parser, right? So is there any foreseeable, let's say, on track, let's say something on your end that you have for other kinds of messages, or so what's the deal?
So at least for the first release, it's going to be anyhow something done in software. So if another project protocol, like I guess Trimble or who else is there who makes GNSS receivers, has a different protocol, you could easily parse them in software. I assume you can extract UTC time and UTC offset from that directly. For the extended design, as a first step at least, we are planning to use UBX, so the MeBlocks ones, just because that's the one that currently is foreseen for the time card. So yeah, I mean, once the source code is there, feel free to extend it for Trimble protocol or some other protocol. But for the initial thing that we are providing as the base system or the extended base system, it will be UBX at least.
David, do you want to ask the question, or you want me to ask it for you? So yeah, so David was wondering, is there intent to translate the software to be done in x86, or is there a possibility to instantiate a small, let's say, processor on the FPGA to do things like that? It's more like, is there room? I'm assuming like there are two folds for this question. One is like, if we can do it on the existing 7th series Arctic Xilinx, or in general. I mean, in general, nothing's stopping you because we're going to release everything open source. But let's say for the Arctic 7, what do you guys think?
Well, it would be kind of a step which is, in our point of view, not really necessary. So the real goal is to get the time to a host system, so PCI via PCIe. So if you have anyhow that connector and you have a CPU there, it would be, in my point of view, a bit overkill to have a soft core CPU in the FPGA basically handle that. So if you want to have that, wait for the extended base system, which would synchronize directly in hardware again. So that is a bit, at least my point of view. I don't know whether Thomas sees it a bit different. But in general, I mean, what you connect to the PCIe part, it doesn't have to be x86. It's a Linux driver, which can also run on ARM or whatever. So the host system doesn't have to be Intel CPU, or it can also be an ARM CPU.
Yeah, in general, I agree with Sven. I mean, it doesn't really go in the direction we would like to go. However, I've also quickly checked the resource utilization. I would say for the time card now, which is, yeah, I would say a bit full with all the additional features, additional cores which we have in. It would be most probably tied to add, let's say, a small microplace. I would assume it should be still possible. But as Sven has also mentioned, we will skip for the base system and also for the extended base system some cores, so there is more room for user space. So if you would like to realize something like that, I mean, it would be of course possible to take, let's say, the UART part in a softcore solution. Yeah. But I would say, as Sven mentioned, it's not really the idea behind it to do this stuff then there.
There is a follow-up question by David, and that is, do you see any compromise in the precision and accuracy? Let's say when you go between hardware to software, software to hardware, anything of that sort, or not?
Maybe a really slight one, a slight decrease, just because of the latency it takes to calculate the adjustments and feed them back again. I mean, in the FPGA, it's kind of immediate. If that takes like 100, let's say hundreds of microseconds, yeah, you're already drifting away with what you basically corrected the last time. So you're always a bit behind, but if you have, for example, a PI servo loop, it will in the end be outcompensated. So not really in that term. So a bit, maybe a bit, but not really that much, I would say.
And I think that's mainly because the characteristics are not changing so fast.
Yeah.
Like, because I mean, you're compensating, let's say, for the short-term stability, let's say, of the main oscillator you have. So another thing that I see value in, let's say, adding a local processor, let's say microblaze or whatever, or even like, let's say, a microcontroller, which was something that we were thinking actually when we were designing a time card, was, let's say, those statistics, those like long-term statistics, they can be performed there. Or in case of when you have two GNSS receivers and you're trying to basically do some voting or, let's say, some spoof detection, I think things will become very valuable if you have the processor local.
But do you want to really do that directly on the time card? You anyhow have a probably much more powerful, and especially with more storage, if you're talking about long-term statistics.
No, I agree with you.
PCIO host side.
But I mean, just as an option, let's say for an application, you prefer to have things regardless of, let's say, the x86 platform is restarting, or I don't know, whatever is going on with x86. So you have higher reliability with this microprocessor running more deterministic. There's no OS, like bare metal, and then you know what's happening.
Yeah, I mean,
there are no restrictions for that. I mean, the interfaces are available, so if someone would like to do stuff like that.
Maybe we need to explain something.
That's the main reason why we are open sourcing this, so we allow everyone to. Yeah.
There is an AXI interface. I don't know who's familiar with that, but it's kind of an on-chip bus, and it's multi-master, multi-slave capable, basically, with interconnects. Yeah, I mean, x86 is one source to connect to our core, to the cores, but of course you can also instantiate a microblaze CPU or a RISC-V or whatever CPU you basically want a softcore CPU in there and talk to the cores as well. Yeah, so it's a shared bus. So
maybe you can quickly go to slide 6. There it's a bit visualized that we have already several bus masters in the system. So this is definitely no issue to, yeah, exactly. On the top you can see UART to AXI, which has an AXI master, a static configuration which has an AXI4 master, and then we have the Xilinx bridge, which is an AXI4 master. So there are already several parts accessing to this AXI interface.
So one more question. Let's say I want to have the entire time card, the SOM part, redesigned based on an Intel Altera FPGA. How much effort should I put in, and how much you guys can help with to basically like reduce parallel work?
I think the biggest pain for that, going to a different FPGA vendor, is on software side, because currently they rely on all of those drivers which are Xilinx specific. So all the cores that we have, so going back to my slide, yeah, that one, so all the blue parts you need to replace by Intel FPGA IP cores. First of all, I don't know whether all of them are freely available for no cost. Yeah, then it's a lot of driver adaptation. From the FPGA perspective, it would be rather simple to replace those cores by Intel IP cores, because that whole part here would be FPGA vendor independent. Of course, we need to change the pinout, and yeah, but the main part is getting the driver up and running with other vendor-specific IP cores.
Just to clarify to everyone, the driver is already open source. It was open source from day one, and the main maintainer is Jonathan Lemon, and you can find it on timingcard.com on the driver side. So perhaps I'm thinking right now, maybe we should have a presentation, let's say, specifically about the driver and what is going on with the driver. Maybe down the road when we get like the community a little bit more engaged with the development of how the sausage is made.
It would be very interesting, especially since we come up now with that core list. If you make the driver generally more generic, you might get also more generic on the vendor specific FPGA vendor specific IP cores. So it might be easier then also to replace those driver parts of it and move to an Intel FPGA device. But yeah.
Also as a like wish list, I like to have PTM, let's say, running between the time card and let's say the CPU.
Oh yeah, we would love to have that, but as you see, PCIe part, Xilinx core, it doesn't support it yet. I don't know
just putting
when
it
they
out
will
to
add
the
it.
universe. So, and hopefully we have the audience here. The
I
universe.
assume that it will come at some point, but currently we're not there. But yeah, that's definitely a really missing feature, because now we have a really accurate time here, but the last inch is basically still not under timed control.
The synchronization on the last inch.
Yeah, exactly.
Anyone related to that, if you like to add something, please feel free, go on mute. Okay, so another question, I guess, let's see, by David. Is it possible for a PCIe device to directly initiate memory transfer to update the host clock, avoiding the host OS from having the query? I think this is more like a DMA thing. Like, is it possible to have something like that?
Yeah, it would be possible to DMA directly into host memory.
Existing hardware, or like do we need some changes?
I think you need some change on the PCIe endpoint bridge part.
It's not the memory map bridge anymore. It's a different kind of PCI Express bridge then. I'm not 100% sure if the Arctic 7 does support it, but
I think it was actually part of the example that Xilinx basically.
Yeah, you're right. You're right.
Yeah, because that was how they were doing the throughput test. They were putting the CPU away, and they were just doing like throughput with the DMA. So let's look into that. I think that's actually an interesting one. It will have, like, let's say, more deterministic latency when you go through. Still not PTM.
I'm not sure whether it is that more deterministic, but because you're updating. you're updating the time there based on what?
You're updating. You're
Often as
basically
possible.
reflecting the values you have on the PHC, which lives in an address, in a memory address on the PCIe bus on the time card somewhere in the RAM. But then, how would you measure it? That's another question.
Yeah, so
So let's see what. Yeah. Okay, David. Okay. Anyone else? Please don't shy. Like, we've been 20 minutes in questions and only David has been asking questions. Should we call names? I mean, there is also a parallel effort to make a light version of the time card, let's say in a smaller form factor, which it's still like work in progress. That's why we don't have that much to present about that. But certainly, once we have this, the FPGA opened, like I'm hoping a lot of, let's say, contributions, a lot of derivatives of the design will be driven by the community, so we can have all sorts of things basically driven from this effort.
Ahmed, I have a question.
Yes,
but
perfect, Hisham, go for it.
maybe general question. We are discussing now in IETF satellite networks and how we can route traffic between one satellite to the other, and how you can deliver maybe deterministic service when you across satellite networks, or even when you integrate this network with terrestrial networks. So can this time card be used in such a kind of use case or scenario?
I mean, looking into the IP cores, if anything is relevant, it's going to be all open source, and there is no limitations. You can use whatever is there if you apply. But the time card specifically, I think, I mean, we have to look into the architecture. Are you talking about, let's say, a constellation of satellites to say what you have, like Starlink?
Yes, you're right. And if you agree, I can refer these guys to your project.
Absolutely.
Okay, good.
This is all open to public anyways, yeah.
Thank you very much. Thank you.
You're welcome. We have also a parallel effort, like we're looking into, let's say, alternatives, or like what we can do basically in general with a GNSS receiver, what we can do with the high stability oscillator, like right now, the atomic clock is almost like a must based on, like, let's say, the design, whatever we have, but that's not really true. Like, we can easily go to a OCXO or other things. So there is some effort also, like we've been working on making adapter boards that they just sit where the atomic clock is, same footprint, but then you can have, let's say, an OCXO, which I mean, we prefer to have the synchronization done in hardware, and we experimented a lot with NetTimeLogic on that. Like, it's always, you get better performance. You perform the synchronization in analog, or like before you come with a quantization in digital, then this gives you a better performance, overall performance, let's say, in your holdover. I don't know if you want to add anything to that, Thomas. Is there anything you want to add to that? I don't know.
Yeah, no, not right now, but yeah, I fully agree that definitely would make sense. I mean, the Mac is also quite costly, so there are attractive options to go for D6O stuff like that. And yeah, this was also shortly popping up again in our mind that this might be very an interesting track to follow up again there.
Also, one more question. I don't know if Julian, are you here? I don't know if Julian is still here. So what does it take, let's say, if we want to convert this time card to a different form factor than PCIe, let's say go for M.2? Like, any roadblocks from your end?
You mean from our end or from?
Yeah. Any, like, in terms of cores?
So what interface are you gonna have to host
You
CPU?
go for the M.2 form factor.
Is that, sorry, I'm not sure that familiar with that. Is that just the form factor and still PCIe?
I think it's also PCIe. It's definitely PCIe. I don't think.
Okay, so yeah, regarding form factor, we don't have any restrictions. So
Yeah,
you can pack it as small as possible as you want, or as big as you want. As long as basically the same interfaces are there. And if you would even connect it to the same pins on the FPGA, you wouldn't even need to adapt the FPGA design. If you change pins, of course, we need to adapt the pin out. But other than that, I don't see anything that would block you from doing that.
I think this was actually what David was asking also, is like, can we run, let's say, the whole stuff, let's say on the FPGA? Let's say we don't necessarily need the PHC, we just need timestampers. So we run the time card without the PCIe, and then let's say have just like a slower bus, let's say I2C or serial port, to just like basically query the timestamps.
So I'm going back to Thomas' slide. So here you see a really slow interface, which is a UART. So there we have it. Once we have the extended system again, where no interaction basically with software is required for synchronization, you will have timestampers. We have a UART to AXI, so we have a small GUI, for example, for the existing design at least. You can access those cores, get the timestamps out of it. Yeah, so as long as the software is not completely involved into that interaction, so that's why we are doing the extended design, then you can have it running standalone again and basically just fetch the time whenever you need, or fetch the timestampers. Yeah. So yeah, of course, that is possible.
And you even don't need to go, so you can also go command line to this interface.
Yeah, currently it's a serial terminal would be enough. The GUI just sends ASCII text there.
So it would be easy from any application via UART to get information from the design.
Just to add to what Sutton was asking, like with an M.2, which is very restrictive in terms of real estate, like you need to have the GNSS receiver and the, let's say, a MAC. So we've been looking into, let's say, high stability oscillators, OCXOs, smaller OCXOs, or TCXO, let's say. And for the GNSS receiver, either they are miniaturized versions of like GNSS receivers, or use some alternatives. Let's say use a UWB receiver, where you have somewhere else a GPS receiver that is sending you the PPS over UWB. So we've been exploring different options for that, if that answers your question, Son.
Yeah, or that goes directly again into the thing why we can feed in PPS and NMEA messages from the outside. So it doesn't have to be on the board. I mean, you could provide the serial data stream and pulse per second via the SMA connectors and use them to synchronize basically.
Yeah, and that is basically the newest addition, that on the SMA, not only, let's say, PPS in and out, you can send this interesting serial communication. It's a,
yeah.
USART.
That's it. So yeah.
Okay, so we are on top of the hour.
From FPGA perspective, this has nothing to do.
Yeah. Okay, so we are on top of the hour. Thank you everyone for attending and engagement and everything around that. So we look forward for the work of the community on this, and we look forward to see all kinds of derivatives, new products, whatever you name it. So thank you very much.
Thank you, and have a good day.
Thank you. Thanks. Bye-bye.
Bye.